Hi, everyone. Welcome to Picking Lockfiles, Attacking and Defending Your Supply Chain. We'll be talking some about supply chains, how software is built and deployed, and how Lockfile tampering in particular can play a role in an attack chain. There are many forms of supply chain attacks, Lockfile tampering being just one. Our goal is to help you understand Lockfile tampering in depth, as well as how to better defend it or add it to your red team tool belt. Supply chain attacks are really nothing new. A military history provides some great examples of what supply chains look like, what they're for, as well as how they can be attacked and defended. Supply chains are in place to move critical assets to the right place at the right time. During World War II, opposing forces would sometimes use inflatable tanks, wooden airplanes, and fake buildings to confuse the enemy and divert direct attacks on the chain of supplies flowing from one place to another. Sometimes these plots were discovered and opposing forces would drop wooden bombs on wooden airfields to jokingly say, hey, we see what you're up to. And in a way, this is similar in a sense to Lockfile tampering, where fake dependencies can be injected into the software supply chain. Why are we talking about supply chains at all? A software supply chain is in essence a sequence of processes in place to promote the production of and distribution of an application. There have been a number of newsworthy breaches manifested through supply chains in recent months and years, and you really can't mention supply chain attacks without mentioning the news stories surrounding them. And news stories like these, they tend to attract the attention of organizations and make them ask the question, hey, what if this happened to us and what would be our response? Packages or dependencies serve as a way for developers to add code to an application for typically a specific purpose without them having to write every single line of code themselves. For example, performing web requests in software is arguably a solved problem. Few developers want to rewrite a web request module, nor should they. So developers would typically pull in a package or a dependency that meets their requirements and install it with a package management tool so that it can easily be leveraged by a team of developers during the software development lifecycle. It's become really easy to pull in code, pull in third-party dependencies and such, but hard to verify the integrity. Our ability to pull in software components has outgrown our ability to verify the changes over time. Supply chains for software can be extremely complex. You have things like CI/CD pipelines, containers, package registries, and the like. With the rise of DevOps and DevSecOps and the like, the tool chains to get software from devs to users can get long and complicated. We won't go into a lot of detail about why supply chains are vulnerable in general. There's a talk by Adam Shaw where he does a deep dive into that specific topic, and it's probably worth your time. But for now, let's focus on one attack involving Lockfiles and understand better what Lockfiles are. It's important to point out that any of the components that we've pointed out here in the slide can contain a Lockfile, and therefore they can be subject to a supply chain attack. Most programming languages and frameworks have a package management system incorporated into their accepted architecture. Each works slightly differently, but the general concept as to why they exist in the first place is the same: to download third-party apps into your application. They each have in common a Lockfile to allow for some level of consistency during the overall SDLC. Our premise is that there are insufficiencies in how package managers verify these dependencies. And we'll go over the elements of a Lockfile tampering attack. We'll cover some red team approaches you can use if you want to test your organizational controls around this type of attack. And we'll look at some custom offensive tooling to help you find the right dependencies to target from the attacker side, and also tamper a Lockfile automatically if you want to do so. We're also going to look at some custom defensive tooling that'll help you defend a Lockfile tampering attack. And I'll turn over to Dennis for a few examples of what Lockfiles are and how they can be manipulated.
Thanks, Greg. I will walk you through the defender side of Lockfile tampering today. And the key message that I want to get across is that Lockfiles are sensitive. Any changes to Lockfiles need to be carefully reviewed. And we will also talk about some good practices for protecting Lockfile integrity in your projects. and also how we can raise the bar for what a successful Lockfile tampering attack could look like. And as Craig already mentioned, I will also have some defensive tooling that can automatically detect Lockfile tampering attempts. But before we go into the details of what Lockfiles are, we quickly introduce ourselves. I'm Dennis Appelt. I'm a staff security engineer at GitLab, working in security research. And what I do is I help engineers write secure software. Craig and I have worked with several development teams, and we want to share with you our experience that we had creating awareness for Lockfile tampering attacks.
Yes, and my name is Greg Johnson, and I'm on the red team at GitLab. And so my job is to break software systems and help make them better.
Okay, let's jump into explanation what Lockfiles are. So when your package manager is installing your application dependencies, there is a certain ambiguity which version of a dependency should be installed. For example, your application might depend on the latest version of a dependency. And what latest is resolving to really changes in different points in time. So latest is a moving target, in other words. And what this results in, if you run your package manager to install dependencies multiple times at different points in time, you will have different dependencies installed on your system. And this leads to inconsistent application behavior. And what Lockfiles get you is consistency here. So let's have a look at how Lockfiles get you consistency. So every time the package manager adds or updates a dependency, it's writing to the log file the exact URL from where it pulled down the source code and the exact version that was installed, so that future installation runs can go back to this information and download again the exact same version of the dependency. Log files are checked into source control, so that future installation runs can pull them down from source control and then work based off the log file. And I really want to stress this point that log files are version controlled, because this is where log file tampering comes in. If an attacker manages to get a malicious modification to log files merged, then potentially attacker control dependencies will be installed on future installation runs. So let's have a look how a log file entry looks like before we talk about how you can temper these entries. So let's assume you use the package manager yarn and you add a dependency called cowsay to my app. If you do that command, then yarn will write the following entry to the log file. Let's go over the single lines in this entry. The first line says for which dependency this entry is for. So this is for cowsay, and then it gives a semantic version range that the log file manager has to resolve at installation time. So not log file manager, the package manager has to resolve it at installation time. In the next line, the package manager notes down which exact version the previous semantic version was resolved to. So in this case, 1.5. The next line is the exact URL from which the source files of the dependencies were downloaded. And the next line is a checksum of the files that have been downloaded from the previous URL for the purpose of integrity checks. And then the next attribute here is about all the child dependencies of cowsay, but we don't need to go through all these entries because they follow the same pattern. So now let's talk about log file tampering. When you look at the log file, there's a message that says something like, this is an auto-generated file. Do not edit this file directly. And this creates the impression amongst developers, in my experience, that it's not possible to manually edit this file, or Jan would consider any manual edits to be invalid and would reject them and not install from such log file. But as it turns out, that's not the case. It's possible to manually edit the log file, and Jan will still accept it as a log file, as a valid log file, and install dependencies from it. And this can be used for logfile tampering. Let's look at an introductory example of how logfile tampering can happen. So here we have another logfile entry. It's for the dependency DOM purify. But if you pay close attention to the resolved URL from where the source code for this dependency was downloaded from, it says DOM purify. So these two letters here, U and O, have been twisted. So what this means that the sources of this other dependency here don't really need to match with what is expected when you would download DOM purify. So an attacker could change the URL like this, and then he also would need to, of course, to upgrade the integrity hash to match the sources that are downloaded from here. But if he does that, and if his change would be accepted into the version control system, then future installations would install the attacker-controlled dependency DOM purify, which might lead to arbitrary code execution. Let's have a look at another example. There are many ways how log files can be tampered, and I just want to give you a brief idea of what's possible. So here in this example, certain attributes in the log file entry are repeated. Here, resolved and integrity appears twice, and just by looking at that log file entry, it's difficult to tell what Jan would do when it's processing this entry. As it turns out, if there are multiple entries, Jan is using the last occurrence of an entry. And here again, it would resolve the dependency DOM purify to DOM purify as and not the intended DOM purify. So here's another example of how log file tampering could happen. In this example, the integrity attribute is removed altogether. And interestingly, Jan is not rejecting this entry. It's still downloading the sources, and it will simply skip the integrity check. So if a malicious log file gets introduced that is not having an integrity hash, that is opening up other interesting attack vectors, where instead of tampering the path of the resolved URL, we could tamper the host of the resolved URL and essentially proxy the request to download the dependency. And since the integrity hash is missing, Jan would not realize that the files have been changed. And this is also not only specific to Jan version 1. So all the examples that I showed you so far was for Jan version 1. In the latest version of Jan, the same basic problem still exists. There are a couple of improvements how log files are handled, but essentially it's still possible to change the resolution to a different dependency. Same for npm v7. The log file entry here looks a little bit different than what we have seen before, but it's all very similar. And here again, you can see that the dependency DOM purify is resolved to DOM purify. And npm will also install that without complaint. And completely different ecosystem, Ruby bundler. So this is for installing gems. Here is an example of installing Rails. And with bundler, it doesn't store the URL exactly where the source files have been downloaded from for a dependency. But what you can do is you can add additional dependencies that actually do not belong in there, and a bundler will still install them. Like here in this example, all the usual dependencies that belong in here for Rails are here. And in addition, also Cause is here. Cause doesn't belong there, but bundler would still install it if he would install from this log file. So now that we've talked a little bit about how log file tampering is happening, I hand it back over to Craig, who will talk a bit more about the attacker perspective.
Yes, so the attacker's perspective of a Lockfile tampering attack is fairly straightforward. The goal is to, as quietly as possible, inject an attacker-controlled dependency into the supply chain without breaking the functionality if possible. meaning there's a need to fully understand the software stack, the architecture, and the build systems that make a target application work. Some package managers have the concept of developer dependencies and production dependencies. And this is important depending on what your target is. So developer dependencies support the development of the application as you would expect from the name. They typically sit on CI servers and developer machines, but don't get deployed to the final production server. Developer machines typically have some sensitive key material, passwords, or information we as an attacker might be interested in. Look at how an application is configured to download its dependencies to better understand which type of dependencies you may want to tamper. Regardless of the target you're after, the goal is typically to gain access to information in order to pivot or escalate privileges. In other words, tampering the Lockfile is probably not going to be the final stop for a live attack. Best practices in the software industry, as Dennis has already mentioned, suggest that Lockfiles should be committed to an SCM repository. So in essence, your attack is going to be somewhat visible. That is, if someone looks at it, which isn't very common for Lockfiles. As we'll see in a minute, Lockfiles aren't very readable, and developers tend to trust a machine-generated file, which isn't unreasonable. But your job as an attacker is to make the Lockfile change look legitimate and incorporate it into a beneficial change. Both GitLab and GitHub hide the Lockfile changes on their diff tab in some way. The change set for even a minor version bump on a single dependency can be quite large. And payloads for this type of attack can vary based on the goal of the attacker. Typically, you'll see some code added to a hooked event that gets raised during the installation process. But that's by no means the limit. With regard to Node specifically, the event hooks available have changed a bit over time. But these changes really have little impact on an attacker's ability to compromise a system with a Lockfile tampering attack. We'll cover some red teaming aspects of this type of attack specifically, as Lockfiles are common components in software architectures. Many software systems these days are polymorphic. And then though the main application may be in Golang or C#, Lockfiles may exist for Node.js in the same ecosystem to enable build and deployment features. Red teaming, you'll obviously have some limitations around the sort of payloads you can logically deploy during the exercise. Know your audience and understand what you will need to show impact. For most, reaching out to an external server with something like a random hash value, for example, will be enough to demonstrate impact. Maybe writing a text file to a specific place on your target system to show potential for arbitrary code execution is also good. We'll show an example of that in just a minute. Your mileage may vary though, so this is probably one of the more critical aspects to consider if you're going to red team with this type of attack. I've included in this slide some information on relevant TTPs in the MITRE ATT&CK framework. There are a lot of ways for a Lockfile tampering attack to happen. It all depends on your target and if red teaming, your organization's tolerance for more ambitious attacks exampled in the MITRE ATT&CK framework TTPs from the previous slide. Something more real world where Lockfile tampering isn't the final stop in the attack chain. Attackers are also looking for opportunities to reduce the footprint during injection. The most subtle footprint of all, regardless of Lockfiles, is an upstream dependency tamper. It simply takes a downstream upgrade to compromise the systems. If during the review process or reviewer diffs or changes, the attack will be in plain sight, but hopefully very difficult to detect. The first step in general is to publish a convincing package on a package management system. There are a lot of details to look for. Author, the number of versions released, download count, naming, publish dates, all of which are typically displayed on a web page related to your dependency, your malicious dependency. Download counts are simply a function of a tar file download or package manager installs. They can be bash scripted to get a closer count. And most of the critical data fields can be manipulated in some way. So keep that in mind. So I want to demo for you a tool called BumpKey. It's an offensive tool to speed up the research process while looking for Lockfile attack vectors and to automate the process of tampering the Lockfile directly to make it more approachable and less prone to human error. So now we'll jump into BumpKey and take a look at its functionality. Okay, so before we dive directly into BumpKey, I want to show you an example of a typical open source application. In this case, Facebook's React, and we'll take a quick look at the package JSON just to see what that looks like. And here we see we have lots of scripts involved and lots of developer dependencies involved. If we just take a quick look at the length of the Lockfile itself, we can see it's 16,000 lines long, which is going to be pretty hard to review end to end for any developer. So what I'll do now is take BumpKey and do a little recon on the React project to figure out what specific dependencies are out of date within that project and some specific details that will help us as an attacker make a decision on which dependency to tamper. So let's take a look at ESLint. What's specified in the package JSON is 770. What's wanted, what's actually downloaded by the package Lockfile is 732. And the latest version is 8.0, so they're a full major version behind. And we get some other helpful details like the URL where the project's located, where you can find bugs and dependency counts. So this one has quite a bit of both dev and production dependencies. So the idea there is the more dependencies that a package has, the more surface area there might be for an attack. You don't necessarily have to tamper a top level dependency. You can tamper a dependency of a dependency, for example. And here we see we've ignored 68 up-to-date dependencies. So for this next example, I'm using the latest LTS version of Node. As I mentioned earlier, some of the hook scripts that are available in Node have changed over time. It doesn't really impact the ability to do the Lockfile tampering attack, but just wanted to show what version I'm using here. And next, we're just going to take a look at a fake application to demo what a Lockfile tampering attack might look like. And this one's pretty simple. It pulls in a single dependency, DOM purify. And it's simple enough where we can take a look at the package like JSON in full and grok what's going on. So here we see our DOM purify dependency. It's requesting 233, and we have defined our resolved URL and integrity hash, both of which are valid. So right now we have a clean Git status history. We have no dependencies installed. And what our malicious dependency will do in just a moment is write a file to temp LOL just to show the propensity for arbitrary code execution. So now what I'm going to do with BumpKey is actually tamper the Lockfile in our fake application and replace the DOM purify package name by package name and replace that with our quote unquote malicious dependency. In this case, DOM purify. Notice the spelling difference. And if we let that run, we'll notice that we've got some diff changes introduced to the package Lockfile. And if we diff those changes, we can quickly see that the resolved URL and the integrity hash have changed. And if I install the dependencies and cat out that file that we expect to see, we can see that it's been written to exemplify some arbitrary code execution as an example.
So now that Greg walked us through the BumpKey tooling, we'll have a closer look at the defender side of Lockfile tampering. So how can you defend your projects from Lockfile tampering? And the key message that I want to get across is that log files are sensitive and all changes to them need to be reviewed carefully. Now that we've talked about logfile tampering and introduced how it works, it might be obvious that this is the case. But in our experience, when we talked to developers, they were really surprised to see that logfile tampering is possible at all. They thought somehow package managers would verify the integrity of the log file, but that's not the case. So how can you protect log file integrity in your projects? First, you should familiarize yourself how your SCM solution display log file diffs. Sometimes it's necessary to take manual action to see actually the diff. Here's an example of how it looks in GitLab. This is a merge request that is changing the yarn log file. And because there are too many lines that have been updated in this merge request, the file is not shown. So you need to click on view file to actually see the changes. Before you inspect log files on your local computer, you should make sure that the content of the log file is okay. Especially you should not install from the log file on your computer without having inspected the file, because if it's actually tampered at the time of installation, it's already might be too late. Another way to raise the bar of what a successful log file tampering attack could look like is to use automated dependency updates. If you stop accepting trivial contributions that just, for example, bump a dependency version, you make it more harder for an attacker to put together a convincing contribution that is containing log file tampering. And there are various bots that can help you with automating log file updates. So this just reduces a very low effort attack vector for the attacker. And here's an example how an automated dependency merge request might look like. This has been created by Renovate bot. Just make sure that if you use this, that it cannot easily be impersonated by an attacker by just copying the layout of the merge request. And also when you evaluate which dependencies to use, you might want to pay attention to how dependencies are reviewing log file changes, because as Greg mentioned, the dependencies that are in the supply chain could also fall victim to log file tampering. Now let's have a quick look at the demo for how to automatically check the integrity of log files. So this is the demo of untamper my log file, and as I mentioned, it's the counterpart to bump key. The demo picks up essentially where Greg's demo ended. We have a tempered log file, and I already installed the dependencies from that log file, and just to show you that it actually worked. So here you can see the file was written to temp. Now let's see if we instead use our defensive tooling on that log file to check the integrity. So how that works is you call the tool like this, you pass in the log file that you want to check, and then the tool goes through each dependency in your log file and it checks that the metadata that is recorded in the log file matches with what is stored in the registry. And if there's any mismatch between the data in the log file and the registry, it will report an error. And here, as we would expect, it reports an error for don't verify because the integrity hash and the resolved URL don't match. I'd recommend to run the tool in a CI job and let it run every time there are changes checked or submitted to your project. So it will automatically fail pipelines if log file tampering is detected. Here's an example for GitLab CI. You can just copy and paste that into your CI config. And then if actually the tool reports an error, you see the pipeline is failing, and this should create enough noise for you to figure out that there's a log file tampering attack going on.
Yes, and for closing words, just a couple of things that I want to mention. both Dennis's tool, Untamper My Lockfile, and BumpKey are open source, and we welcome contributions. From a red teaming perspective, there's just a couple of closing points that I want to mention. Leadership communication and careful control thereof is probably one of the more important aspects if you plan to red team this type of attack. Keep the goal in mind, which is to test the controls and make them better, whether you're focused on the defensive side or the offensive side. Be aware that there can be some social aspects in relation to this type of attack. Reviewers will likely want to talk to you about your changes, be able to speak to them and justify them. And there can be an element of social engineering in tandem with this type of attack. So that's something to be aware of as well. In closing, thank you for listening, and we welcome your contributions.